Okay, so here we're looking at another example, doing volumes of revolution. And this time we're looking at the region bounded between these two curves. We have y equal to x squared, y equal to x. And in this scenario, we're going to be rotating that region around the x-axis. Okay, so when you, in the future, start doing these, you won't need to actually be sketching the three-dimensional region, but for this one, we will take a look once more at what this would look like if you rotated it around. And what you'd end up with is something roughly like this. Okay, you'd end up almost with this conical figure, except that it does have sort of this empty interior. And again, what we're looking at doing, similar to what we were doing with discs, is that we're going to do a cut that is going to be perpendicular to the axis of rotation. So in this case, we have an axis of rotation that is horizontal. Okay, we are rotating it around the x-axis. So we will be doing a vertical cut. The only difference between this method, washers, and the previous method, which was discs, is that you'll notice here our region that we're rotating is not entirely bounded by the axis of rotation. There's actually that gap right here between our region and the axis. And so that's going to be important over here when we've rotated it around. If I go to do my vertical cut perpendicular to the axis of rotation, you'll notice that that cross-sectional cut doesn't actually form a disc. So what we actually end up with, if we do our cross-sectional cut, let's suppose that it looks like this. And it's going to have, because it is a vertical cut, it's going to have a thickness again of delta x, except that when we remove that portion, it's not going to be a disc. What we're going to end up with instead is going to be a washer. So really, what we end up with is one disc, which has had a smaller disc removed from it. And so really that will change the volume, that is going to change the area, but nonetheless the thickness of the washer is going to remain delta x. This is going to be what we refer to as our washer. And we remember for discs and in general for volumes, what we are looking at doing is integrating the surface area, and our smallest x value will be a, our largest x value will be b. So now when we look at this washer rather than the disc, we want to know what is going to be this surface area. And there's only actually going to be one small difference. What we'll do is we'll find the surface area of the larger disc, and then we will find the surface area here of the smaller portion that has been removed, and we will subtract that. So what we end up getting for the surface area of this washer is that the area is going to be pi multiplied by the radius of the outer disk. So if we have this, our axis of rotation, going right through the middle of our washer, the radius of the outer disk will be the distance from the center here, the axis of rotation, all the way to the outside of the washer, and we can call that, let's say, R2. So in that case, the surface area then of the larger disk will be pi multiplied by R2 squared. And then we would like to subtract from that the surface area of this smaller disk that was removed. So if this is going to be the radius of the inside disk, then we're going to be removing the area that is pi multiplied by R1 squared. And so really the surface area for a washer is going to be given by pi multiplied by the outer radius squared minus pi multiplied by the inner radius squared. And this is essentially what we're going to be using. So now all that remains is to figure out for our situation what is going to be R2, what is going to be R1. What's going to be the radius of that outer disk, what's going to be the radius of the inner one. So if we come back over here to our picture, we can try to label it on here, but it is going to get quite a bit more cluttered. You'll notice again, similar to this washer that we drew over here, we have our inner radius would be the distance from this function down to the x-axis, to that axis of rotation. And then for us, we have the outer radius would be the distance from right here all the way down to the axis of rotation. So that would be R2, and this would be R1. However, this is where you'll start to notice that drawing it onto the three-dimensional image does get a little bit cluttered, and over here with the two-dimensional image, this is really all that we need. If I go and sort of draw this cross-sectional cut, this vertical cross-sectional cut, but if I draw it over here on the two-dimensional image, then you'll notice this washer is actually just represented by a single rectangle. Okay, and in fact, if you take that rectangle and you rotate the rectangle around the x-axis, you'll notice that's actually going to be over here generating your washer. So R1, the distance from this inside curve down to the axis of rotation, is more easily seen over here in the two-dimensional image. That is R1. And then R2, the distance from the outer edge of our washer to the axis of rotation, again over here in the two-dimensional image, R2 is much easier seen. So now we can find R1 and R2. And let's start with R1. If I take a point here on this curve, similar to how we have done the previous examples, I know that the height from this point down to the x-axis is given by the y value. So in fact, when I go here for R1, we could say that our height is going to be y1. And so the first radius is just going to be the y value of that first point. If I go to R2, you'll notice that the height there is just going to be the y value of that point, and let's give that point coordinates x2, y2. So R2 is going to be y2. And that's fine, except that you will notice when we're looking at either this two-dimensional image or the three-dimensional image, the thickness is supposed to be delta x. Our integral in the end is supposed to be with respect to x because we did that vertical cut. And so our radii are both right now in terms of y. This is a problem, but it's not a large problem. What is y1 equal to in terms of x? What is y2 equal to in terms of x? If I look at y1, y1 right here is our parabola, and y1 will be equal to x squared. R2, we have y2. That's this right here, and y2 itself is just equal to x. And again, why do I not put here x1 and here x2? Well, you'll notice the x values along these 2 points are the same. It is simply the y values that are different. So we have R1, we have R2. Now we can go and plug it in. We get that our volume is going to be pi multiplied by R2 squared minus R1 squared. We are integrating with respect to x, and we need to figure out what our limits of integration will be. So, knowing R2 is x, this becomes x squared. R1 is x squared. Integrate with respect to x. What is the smallest x value on our region? The smallest x value here is 0. Over here is 0. Again, you'll notice we don't actually need the three-dimensional image. It's enough just to have this two-dimensional. So we have the smallest x value is 0. Largest x value on our two-dimensional region is going to be given by this point right here. This is the intersection between the curve x squared and x, which is just going to be the point 1, 1. And so there, smallest x value is 0. Largest x value right here is going to be 1. And this value, again, we won't do the actual calculations, but this integral would represent the area, the volume of this three-dimensional image, which if you calculate it, you'll end up getting 2 pi divided by 15. And that's it.